In Chapter 13, we're going to look at the gas laws and go through the gas laws of Dalton, Charles, Boyle, Lussac, Avogadro, the combined gas law, and all of these laws are actually derivatives of the ideal gas law. We'll do some gas stoichiometry, and we'll talk about deviations from ideal gas behavior. So we're going to be going through a number of gas laws in this chapter, learning all the different relationships between the four gas variables: pressure, volume, temperature, and number of moles. And since we have number of moles included, we're going to be able to get a relationship between moles and volume at a standard temperature and pressure and do a lot of stoichiometry with that. So we'll be bringing back stoichiometry in this chapter. Before we can really go into a lot of detail, though, on the various gas laws, we need to have a background in the one variable that we're not as used to working with, and that is the variable of pressure. Pressure, by definition, is the force per unit area, the force that's exerted by a surface. If you were to take the equation, and you'll do this in physics class next year, pressure is force divided by area. You have a lot of experience with this concept of pressure. One of the analogies or examples I like to use a lot is if you got stepped on by someone wearing normal shoes and the same person wearing cleats or high heels. You know intuitively that getting stepped on by the person with cleats or high heels would be a lot more painful. Each person is exerting the same amount of force down on your foot, assuming they step in the exact same way. When that force is coming from their weight, their force of gravity. So the weight of that person is being pushed down on your foot. So let's, for this example, make the assumption that they're stepping with one foot and all of their weight is on that foot. So that force is staying the same. Now, when someone steps on you with flat shoes, the area over which that force is exerted is much larger than if they step on you with, say, the heel of a high heel or cleats, where that area of the foot has been drastically reduced to a much, much smaller area. So you're dividing by a much smaller number, you get a much larger pressure. And that's why it's a lot more painful to you, even though it's the same amount of force. When we think about gases exerting pressure, we are thinking about the same thing of a force being exerted on a surface. So let's talk about how that force exists in the terms of a gas. Now remember, gases are particles moving at a very high speed that are spread out from one another as much as possible. They're going to be the highest speed particles. They have the highest temperature for that substance. Remember, temperature directly relates to the motion of the gas particle, the speed at which it's traveling. So, as gas particles move at a very high speed, they're going to collide with the surface of whatever container that is holding that gas, whether that container be your lungs, that container be the room you're in, that container be a balloon, a jar, or a flask in the lab. They're going to exert pressure as they collide with the surface of that gas and exert a force. The more collisions that you have, and the area over which those collisions can occur will affect the pressure. Since pressure is force per unit area, the main SI unit is the unit of pascals. And air pressure is going to be measured with a barometer. Pascal for pressure will be the symbol capital P, lowercase a. Now, a barometer is the main item, the most common item used to measure pressure. And you actually hear, if you listen to the news a lot, the idea of barometric pressure. Now, the way a barometer works is this basic setup in this diagram from your book. Air, the air that's all around us from the atmosphere, is exerting pressure on us as those gas particles collide with us, same way that they'll be exerting pressure on this pool of mercury. So this is pressing down on the pool of mercury. And we've got, so these arrows here, this is that air bouncing off the surface as it collides with the surface exerting pressure. That pressure forces the mercury up into this tube. Mercury will rise up into this tube. There's no gas here exerting pressure. This is an empty space, vacuum, with no particles contained inside. It pushes the mercury up into the tube. Counteracting that is the weight of the mercury. The fact that the mercury column is being pushed down by the force of gravity. So we have the force of gravity pushing down on the mercury column. We have the air from the atmosphere pushing up on the column, causing the column to be forced up. And they reach an equilibrium, a balance, so that the height of that mercury column can be determined. Standard pressure of the atmosphere at sea level causes this mercury to go up 760 millimeters. Now, we refer to one of our standard units of pressure as an atmosphere. Since we are on Earth and we have the atmosphere exerts 760 millimeters of pressure. It pushes a column of mercury 760 millimeters up into the air. That gives us two of our common pressure units. There are actually 5 that we are going to work with. 1 atmosphere is equal to 760 millimeters of mercury. We also have pascals, that SI unit we talked about earlier. The SI unit is relatively small, so we generally deal with kilopascals, and 1 atmosphere, or 760 millimeters of mercury, is also equal to 101.325 kilopascals. Those 3 are also equal to 760 torr. And our last pressure unit, PSI, pounds per square inch. The English units of pounds for force, square inches for area. So when you do force divided by area, you get pounds per square inch. In the standard SI units, when you take that force divided by area, force is given in the units of newtons, area is given in the units of meters squared. So you do newtons per meter squared, and those all relate. We won't use newtons per meter squared in this class, but when you get to physics, you'll talk more about that. So we have 5 different units: atmospheres, millimeters of mercury, kilopascals, torr, and PSI. These 5 are related by this conversion factor that you need to know. And you can make any conversion factor you'd like of any 2 of these units using this relationship. So let's look at some examples of that. Convert 105.2 kilopascals to atmospheres. And we're going to set this up, factor label method, just like we've always done. We want to cancel kilopascals and solve for atmospheres. Now if we go back to our previous slide, we remember that 1 atmosphere is 101.325 kilopascals. So the relationship we can put in here is 1 to 101.325. We're going to divide 105.2 by 101.325. And we get 101.03824, and we're going to keep 4 significant figures just like we started with. So 1.038 atmospheres. 0.995 atmospheres is our conversion factor. We want to get rid of atmospheres. We want to go to millimeters of mercury. Our conversion factor, 1 atmosphere, is 760 millimeters of mercury. We get 758.1 millimeters of mercury. Here we have 774 torr, and we want to go to kilopascals. Try this one on your, press pause here for a second, try this on your own, then press play again to see my answer. So we have 774 torr. We want to cancel torr. We want to go to kilopascals. So we know from our conversion factor that there's 760 torr for 101.325 kilopascals. So 774 times 101.325, and then that divided by 760, we get 103 kilopascals. 3 significant figures because that's what we started with in our original number. One last one, 28.21 psi to atmospheres. Go ahead and press pause, try this on your own, come back and press play when you're ready to watch the answer. So we're going to cancel psi, go to atmospheres. We go back to our conversion factor, 14.69 psi and 1 atmosphere. So we're going to get 1 atmosphere and 14.69 psi. We get 1.92 atmospheres. 1.92. Oh, 4 significant figures. So those are basic conversions of pressure. Pressure is force per unit area. And we should also understand the basic working of a barometer.